So see here. So now capacitors in series and capacitors in parallel. Okay. So when we can say the capacitors are in series, two capacitors are said to be in series if they are connected across two endpoints such that the charge remains same and the potential across the combination is equal to the sum of the potential across each combination. Okay. So when we can say the capacitors are in parallel, the capacitors are said to be in parallel if they are connected across common point, okay, such that the potential remains the constant and the total charge stored in the combination is equal to the sum of the charges on each capacitor. Okay, so here, so now expression for the equivalent capacitors of two capacitors in series. Okay, so I will take a two capacitors in series. Okay, so previously I told the capacitors are said to be in series if they are connected across two endpoints. This is one the endpoint, this is another endpoint. Okay, so and it is connected to a battery. Okay, see now here charge remains constant. Okay, I will write it as so Q and Q. Okay, so this one is positive charge, this one is negative charge, so this is also positive charge, and here there is an accumulation of negative charge. Okay, so here potential is here V1 potential, here V2 potential, and the total potential here is V. Okay, so it has a capacitance C1 and it has a capacitance C2. Consider this as capacitor A and it has a capacitor B. Okay, so we know that capacitance of the capacitor is given by C is equal to Q divided by V. Okay, so previously I told for the capacitors are in series, the potential of the combination is equal to the sum of the potential across the each combination, that is V is equal to V1 plus V2. Okay, so call this as equation 1. Now I need to calculate the V1 and I need to calculate the V2. Okay, so now here from this expression V becomes Q divided by C. Okay, so V becomes V is equal to Q divided by C. For V1 it will becomes Q divided by C1 and V2 becomes Q divided by C2. Okay, now substitute here. So V becomes, so V is equal to V1 means Q divided by C1 plus Q divided by C2. Okay, so here Q constant, sorry Q common, so remaining terms is 1 by C1 plus 1 divided by C2. Okay, call this as equation 2. Okay, now this combination, these two combinations are replaced by the single capacitor which having the same capacitance as before. Okay, now it has only single equivalent capacitor which has the same capacitance as that of 2. Okay, so here CS, I will write it as CS. Why? Because capacitance are in series anta. Okay, so here this is positive charge, here this is negative charge, and this one is potential V. Okay, okay, now for this one, so what is the value of V now? So V becomes, so V is equal to Q divided by CS. I will write it as CS. Why? Because capacitors are in series. Okay, so call this as equation 3. Okay, so if you see the equation 2 and equation 3, LHS are equal, right? So LHS are equal. So what we have in RHS? So in RHS we have Q. See here. See now in RHS we have Q by CS. So Q divided by CS is equal to here RHS term. So Q into 1 divided by C1 plus 1 divided by C2. Okay, so QQ cancel. 1 divided by CS is equal to 1 divided by C1 plus 1 divided by C2. Okay, so this is the expression for the capacitance of the two capacitors in series. For the three capacitors, it will become 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 divided by C3. Okay, so now expression for the two capacitors, equivalent capacitance of two capacitors in parallel. Okay, see now for the parallel, so we'll take two capacitors in parallel. Okay, So previously I told two capacitors are said to be in parallel if they are connected across common point. Okay, so this is one common point. So call these capacitors as A, this one as B, and it has the charge plus and it has a minus. So here also same, and it has the potential V. It has so positive and negative charges. Okay, so here potential remains same here. So here also V, here also V. Okay, so charge is here is Q1, here also Q2, and capacitance is C1 and here is C2. Okay, so previously I told the capacitors are said to be in parallel if they are connected across common points such that the potential remains the same and the total charge stored in the combination is equal to the sum of the charges of each combination. Okay, so Q is equal to Q1 plus Q2. Now I need to calculate the Q. Okay, so I know the formula, C is equal to Q divided by V. Okay, Q becomes CV. So Q becomes CV for capacitor 1. Q1 becomes C1 V1. I should not write V1. Why? Because it is constant. Okay, for Q2 C2 and V. Okay, so call this as equation 1, call this as equation 2. Now put 2 in 1. Okay, so I will get Q is equal to Q1 means C1V plus Q2 means C2 into V. Okay, so Q is equal to, here V constant, I will get C1 plus C2. Call this as equation 3. Okay, so now if these two combination of the capacitors having this capacitance, it is replaced by that one equivalent capacitor which having the same capacitance as 2. Okay, so it has the charges positive and it has the charges negative, and this is V, it has a potential V. Okay, here I will write it as Cp, capacitors are to be in parallel, Cp, and it has a charge Q and it has a potential V. Okay, so now, so what should I write now? So C is equal to, so Q is equal to C into Vp. Okay, so capacitors are in parallel. Okay, so call this as equation 4. If you see the equation 3 and 4, LHS are equal. Okay, so LHS are equal. We can equate the RHS I have Cp into V is equal to V into C1 plus C2. Okay, here V cancel, so Cp becomes C1 plus C2 plus C3. Okay, so this is the expression for the two capacitors are in parallel, and this is for the three capacitors are in parallel. Okay, so previously I have written P here, so that is actually wrong. Okay, so you need to write Cp here. Okay, so thank you. So this much for this chapter. So next in next upcoming videos I am going to solve all the numericals from all the topics, and I am going to solve the KCET as well as NEET and JEE questions also. So try to subscribe for this new channel and support me. Thank you.